We're going to do an example now that uses the transformations that we talked about yesterday in the notes. You might want to recall that we concluded that when we add or subtract something to the data, every data value is just shifted left or right by the same amount. So the measures of position all change, but the measures of spread do not, because the data values are still spread the same distance apart from each other, just shifted left or right. But when we multiply, it serves to stretch out the distribution, or if we divide, it would compress the distribution so that the spread actually changes as well as the measures of position. So keep that in mind as we do this example problem. A business in a large city keeps track of the number of miles its employees travel by taxi on company business in the city. The distribution of miles traveled by taxi during one particular month is shown below, along with the summary statistics. So we have a histogram and a box plot, both showing the majority of taxi rides are fairly short, a little bit skewed to the right with some high outliers. We have over here the mean, standard deviation, 5-number summary, range, and IQR of these data. Now let's say the financial department wants to know the summary statistic for the cost of the taxi rides. The taxi fares are computed as follows. The fare is equal to $3, just for getting in the taxi, plus $2.50 times the number of miles traveled. I got this information online, and this is pretty current for New York City. Actually, New York City has a much more complicated way of determining taxi fares. They actually charge a different number, a different amount for the number of miles versus the amount of time standing still, like waiting in traffic or at a stoplight. But we're just going to, this was a pretty good average of what they had, so we're going to go with this. Now, given the summary statistics here for the number of miles traveled, how would the summary statistics change if instead we were looking at the data for the cost of each of these taxi rides? So we're going to take each one of these data values, theoretically, you don't know what they are, but theoretically, if we took each one of these data values and computed the fare for that number of miles, then how would the summary statistics change? So it might be a good idea to kind of pause the video and sort of think about that for a minute, maybe look back at your notes and see if you can figure out specifically mean and standard deviation. What would be the mean of the taxi rides? What would be the standard deviation of the taxi rides? Here are the mean and standard deviations of the taxi rides. Now, if you had 889 and 816, you made a very common mistake. You just applied the formula for fare to the mean and standard deviation that were up here. So to get the mean, $8.89, I substituted 2.35545 miles into this fare formula, so 250 times that number plus the $3, and then rounding it to the nearest cent was $8.89. But that is not what you do for the standard deviation. The mean is a measure of position, so it is affected both by adding and by multiplying. But the standard deviation is a measure of spread, so it is not affected by adding. You do not add the $3 on, you only add the 250 times the standard deviation. So we have to differentiate between measures of spread and measures of position. So there are two other measures of spread here. So let's kind of think about what we would do to figure these out. So if I go ahead and take each of these values for Q1, median, Q3, maximum, and the minimum, those are all measures of position. To figure out those in fare instead of in number of miles, we're just going to take each one of those values, substitute it into the fare formula, and calculate. So for example, it would be $3 plus 250 times 0.75, $3 plus 250 times 1.2, etc. If we do that, these are the values that we get. We get $4.88 here. For Q1, we get $6. For the median, we get $7.50. For Q3, we get $9.13. For the maximum, we get $28. Okay, now, let's just think about the IQR. The IQR is Q3 minus Q1, which is $3.13. got a little extra dot in there that's not supposed to be in there. Let me back that up here. $3.13. Now, if we were going to if we take the IQR 1.25 and put it into, multiply it by 250 and add $3. So let's do that on the calculator. I want you to notice here, if I put the 1.25, which is the IQR of the data in miles, and I put it in the formula for fare and do 3 plus 2.5 times 1.25, I get 6.125, which is clearly too big for the IQR. The IQR is just 2.5 times 1.25, or 3.125, which rounds to 3.13. So the spread is not affected by shifting the data right and left. It's only affected by multiplying the data. So the range as well is only going to be affected by the multiplying. So 3 plus 2.5 times 9.25. We don't do the 3. We just do 2.5 times 9.25. And that would give us our range. So if we do so if we look at the range, $28 minus $4.88. So let's do that on the calculator. $28 minus $4.88. And that if we do the given range, which is 9.25, 9.25 times 2.5, and don't add the 3, notice we get the same thing, the 23.12, 23.125. Okay, so that is just confirmation that we do not add when we change the measures of spread. So let's just kind of summarize here. So measures of position, to calculate those, we're going to do fare equals $3 plus 250 times number of miles. And those are going to give us different measures of the fare. But measures of spread, we are just going to do 2.5 times the number of miles. So this is going to be a spread like IQR, range, or standard deviation. So those are all going to be measures of spread only. Now, this is leading us to an important conclusion here. We're going to talk now about standardizing scores. So when we standardize all of the fares, what would be the shape, center, and spread of the distribution? Well, standardized scores are z-scores. A z-score is computed by taking a data value, which I'll represent by x, subtracting the mean of all the data, and dividing by the standard deviation. So in the case of the fares, z is going to equal, and we've got it up here, x minus $8.89 divided by $5.16, which is the standard deviation. And we're going to investigate for a couple specific values of x what the z-scores are. And we did this using our height, and we each would put in our height, subtract the mean height for our particular gender divided by the standard deviation, find our z-score. I'm particularly interested in what is the standardized score for the mean. So in for the mean, x is $8.89. And you're going, this is ridiculous, this is so obvious, but we're still going to go through the process. $8.89 minus $8.89, all divided by $5.16 is 0 over $5.16, so $0 over $5.16, which is just 0. So this is saying, recall that the standardized score is the number of standard deviations from the mean. So the mean is 0 standard deviations from itself. Okay, so that the mean of a standardized score is always going to be 0. Now I want to find the standard deviation of the standardized fares. So the standard deviation would be the value that would be one standard deviation above the mean. So I'm going to look at a taxi fare that is one standard deviation above the mean. So we're going to say x is equal to the taxi fare that is 1 standard deviation above the mean. So in this case, x is going to equal $8.89 plus $5.16, which turns out to be $14.05. So if x is $14.05, what would z be for that particular value? So I'm substituting 1405 minus 889, dividing it by 516. Well, to nobody's surprise here, when I subtract 889 from 1405, I'm going to get 516 because that's how I got it in the first place. That's I added 889 plus 516 to get 1405. So now we have $5.16 over $5.16, so z is equal to 1. Notice, remember that we have no units on here because the dollars cancel out in this case. The units in the numerator and denominator will always be the same when you do a z-score, so they will always divide out and give you a unitless measure for the z-score. So this says the mean of the standardized fares is 0 and the standard deviation of the standardized fares is 1, which makes sense because this says I am 1 standard deviation above the mean. Okay, taxi fare that is 1 standard deviation above the mean, this is 1 standard deviation above the mean. That's what a z-score denotes. Okay, so we can summarize that in this case, this distribution of standardized fares z-scores has a mean of 0 and a standard deviation of 1. And what about its shape? Well, the shape up here is skewed to the right with 4 outliers. It is still skewed to the right with 4 outliers. And unimodal. I'm going to go ahead and put that in because a lot of you forgot to write that before. I don't want to forget to write that. Skewed right and unimodal with 4 outliers. So the shape is no different than it was before. Now, in general then, we can say any distribution of standardized scores has a mean of 0, a standard deviation of 1, and no change in shape. This is an important result. I want to go ahead and look at the calculator just briefly and show you that actually that all is true. So if I go to my calculator here and I go to my document that I'm in, current document, okay, here's the taxi fares, or here's the taxis in miles, here are the taxi fares, and this is the standard deviation. These are the standardized scores or the z-scores for all the taxi fares. So you see right here, I just I took taxi miles times 2.5 plus 3 and I got all the taxi fares. And here is the standard deviation. I took the taxi fares minus the mean of the taxi fares divided by the standard deviation of the taxi fares and got all the z-scores. So if we look at some of the graphs I've made here, here is a graph of the standard deviation of the scores, and if I put this in terms of a histogram, okay, you can see that the histogram, if I made the bars the same shape, which I need to do, so let me make the bars to match what I had before, like half of there. So basically, we're having the same shape that we had before for the histogram. Okay, I made my bars just slightly, the width is probably not matching exactly what I had before, but there's histogram, still unimodal skewed to the right. If I turned it into a box plot, okay, looks exactly the same. Now, if I found the summary statistics, the one variable stats for the z-scores, you can see that the standard deviation is 1, okay, or it's pretty close to 1. The x bar, that's kind of a weird number, but I wanted to point out to you what this is: -1 times 10 to the -15th. So this number is 0.00004, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 1, 8, 1, 8, 1, 8, blah, blah, blah. So this is, and there's a negative sign in front of it, this is supposed to be this is your calculator's way of rounding to 0. So basically your calculator has computed that the mean of the standard deviation, the mean of all the standardized scores is 0 and the standard deviation is 1. And the shape of it is unchanged. So this does work, and this is going to lead us into a really important result with a very important model that we're going to be talking about later in Chapter 2.